Hello fellow problem solvers. So they're going to be doing a technique in enumerative combinatorics, namely this problem from one of my country's introductory competition levels. And I suggest you try this nice problem out, especially if you're new to combinatorics or just getting started. Just try this out for a minimum of 15 minutes, like ideally anywhere from 30 to 90 minutes. I wouldn't spend more than 2.5 hours on this problem. But if you'd like to go along with us, give this a go. What are your first ideas? Take 5 minutes. And now let us begin. So, find all functions from the set 1 through 6 to 1 through 6 such that f of x is equal to x. So, for every single x. So we have one of two options for every x, right? We can have, for every single x, we can have either f of x is equal to x, or we can have f of x is equal to y, and then f of y is equal to x. And this satisfies also the thing for both x and y. So we can either pair up numbers, or we can have them stand all by themselves on their own 2 feet. So we can now proceed immediately to counting, but if that's too difficult, and for me, I'm a bit out of practice, out of shape, so I'm not sure if I really know how to do this immediately, I'm going to do something which is a general problem-solving heuristic that's going to be much more helpful than just solving a problem, and that is play around with small cases to develop a sense of what's happening. So instead of, let's say this is A6, let's go with A1 being set 1, A2 being set 1, 2, A3 being 1, 2, 3, and you get the idea. So for A1, and let's call the number of functions N1. Okay, we're going to find what N6 is equal to. So for set 1 to 1, we only have 1 goes to 1, so there's only one function. Okay, let's go to set A2. How many functions do we have now? Well, we have the function that takes 1 to 1, 2 to 2, and the function that takes 1 to 2, and 2 to 1. So that gives us a total of 2 functions. Okay? So maybe I can also say f of 1 is equal to 1. This is one function, this is our solution. And then here our solutions are f1 is 1, f of 2 is 2, and f1 is 2, f2 is 1. Okay, now let's go to the set with 3 numbers. Now we're getting up to higher levels of complexity. So now here we have, what are the functions? Let's write them up. So we have f of 3 goes to 3, and then what? And then we have these 2 functions for the other 2 f's. So we have 2 functions. And then if f of 3 is equal to 2, that makes f of 2 is equal to, what's it called, 3, and then we have this many functions. We have 1 function, and then f of 3 is equal to 1, and f of 1 is equal to 3. Again, we have f of 2 is equal to 2. We only have 1 other function, so n3 is equal to 4. Interesting stuff. Let's continue. A4 is going to be set 1, 2, 3, 4. And if you haven't done this, if you haven't played with A4, pause here. That's a nice chance to pause for 10 minutes and determine what N4 is equal to. Okay, so let's continue. Well, we can have, okay, f of 4. If f of 4 is equal to 4, then I have an extra n3 functions, which is 4 functions, right? So for any single one of them, I have my thing. If f of 4 is equal to 3, then I have f of 3 is equal to 4, and I have n2 functions. If I have f4 is equal to 2, I have an n2 functions. f4 is equal to 1, I also get n2 functions. This is 2, 2, 2. 4 plus 2, 2, 2, 2, 2 is, that's an extra 2. That's n4 is equal to 10. And I legit just continue like this. And this might show a different type of, these are 2 different separate solutions now that I'm thinking about it. Is this one is showing how we can think of now n5 is going to be what? It's going to be, if f of 5 is 5, we're going to have n4 functions. And if it's not 5, f of 5 is either 4, 3, 2, or 1. And for any single one of those, we have an extra n free functions. That's 4 times n free. So that's 10 plus 4 times what? 4 times 4, 16, which is equal to 26. And then n6 is going to be equal to n5 plus 5 times n4 by a similar reasoning. So n5 is going to be 26 plus 5 times n4 is 50, which gives us a grand total of 76 such functions. And this solves the problem, but but now let's go at it in a different direction. So a different direction is, okay, let's say we care about how many pairs of numbers there are and how many singular numbers there are. Okay? Enough about this back and forth. Like, I like this sort of building up inductive proof. I didn't figure it out until I pressed record now. But let's go now with this proof of, let's figure out exactly how many such pairs there are. And the answer to that is, well, let me just clear this up a bit. And this proof is going to look at how many ways can we pick. So we're going to have these numbers that are either go directly to themselves or that are paired up. Okay? So let's call the numbers that are paired up. They are in the set F. The reason I'm saying set F is this is the set of fixed points, right? Because this is like what they're known in the terminology, the set of fixed points. And then the complement. This is going to be the set of, let's say, non-fixed points. So say N. And F union N, fun, is equal to A. I wish this set A was called math. That would be corny and cheesy, but nice. So fun is A. F union N is equal to A. So what's it called? Now what do we have? So the first case is if F is empty. So then there are no elements whatsoever that are fixed, which means we only have 2 paired numbers up. Now, if we have 6 numbers, right? We have numbers 1 through 6. In how many ways can we pair up these 6 numbers? Okay, and there's a couple of ways to think about this. One way to think about it is, okay, in 6 numbers, in how many ways can I choose the first pair? Well, I can choose the first pair in 6, choose 2 ways. Okay, the second pair, I'm left with 4 numbers. I can choose it in 4, choose 2 ways. And then the third pair I can choose in just choose 2 ways. Now, what's the trouble? What if I pick the same pair? What if I first pick the pair 1, 2, and then I pick the pair 3, 4. Okay, then I pick the pair 5, 6. Okay, this is my first choosing, second choosing, third choosing. But what if I first picked 3, 4, then 1, 2, then 5, 6? I'd be counting the same thing twice. And how many times would I be counting the same thing? I would be choosing 5, 6, 1, 2, 3, 4. Well, the number of ways I can pick the same thing twice is the number of ways to take 3 pairs and what's it called, shuffle them. How many different shufflings I can make? And I can make like 1, 2, 3, 1, 3, 1, 3, 2, and then 2, 1, 3, 2, 3, 1. I can have 6 of them. So, or 3 factorial. So it's this over 6 many ways that I can pick these pairs. And this gives me the number of, what's it called, these functions f, if I have 0 fixed points. Right, I cannot have 0, so like n is even. So f must be even as well. So let's say that now if the size of f is equal to 2, then what do? Pause for 5 minutes and think about it. And here's the next step. I can pick these 2 elements in 6 choose 2 ways. Again, right, I can pick these 2 fixed elements in f in 6 choose 2 ways. And for every 2 elements I pick in my fixed, how many ways can I form these pairs in f? Well, I can form them in 4 choose 2 times 2 choose 2. Right? Now for every pair that are fixed, I have these which are not, which gives me a total of this times a half, because I could be ordering them in a different way. So if the size of f is 2, I have this many ways to determine this function. Now, if the size of f is equal to 4, then how many ways do I have? If you haven't paused with this, I suggest, try to do this for 5 minutes or so. 4, how many ways can I pick the 4 fixed elements? Well, I have 6 choose 4. And for those 6 choose 4, there is only one way I can deal with those two in n, right? One goes to the other one goes to itself. Nothing really changes. So this is just 6 choose 4 ways. And now what if f is equal to 6? Well, what does that mean? That means every single one of them is fixed, so then there's one way. That's like that. There's not, the n is empty, so there's not much counting to be done. And so the total number of functions f is this plus this plus this plus this. And now we calculate that. The most fun part, yay. So what is this? 6 choose 2. Okay, we'll do the 6 choose 2 is 6 times 5 over 2 times 4 times 3 over 2 times 2 times 2 over 2 is just 1. All divided by 6. 6 cancels out, this cancels out, so this one is 15. Now let's do this number. So it's 6 times 5 times 4 times 3 all the way over 4 times a half. This cancels out, makes it a 3. 15 times 3, 45. Okay? This is just 6 choose 4, which is the same as 6 choose 2. It is 6 times 5 divided by 2, which is again 15. And now we're going to have 1, so it's like 15 plus 45 plus 15 plus 1. So 15 plus 45 plus 15 plus 1 is a total of 60 plus 16, which is 76 different ways we can choose this function f. This finishes up our problem, and I want to show you like these two approaches, these two different ways of thinking, like immediately counting up everything, which is okay, it's doable like this, or going at it the building up approach, like how can I build up, build up, build up? And there's like this nice recurrence relationship, and this, I think, building up approach is more generalizable. The fun way, F union N is A. I'm still happy about that. The fun way is a technique that can be used in other problems as well. It's just a good thing to know how do you count these, how do you count things, right? 1, 2, 3, 4, 5, 6, and we're done. And as always, thanks for problem solving.